Okay, so right now it is 6:04, so we're going to stop at 6:54. Let me paste the first problem. Okay, and you can go ahead.
So let me read through the question.
Sure.
Given an array of integers nums sorted in a non-descending order, find the starting and ending position of a given target value. If the target is not found in the array, return -1, -1. Or if you find it, okay, we have to find this in O log n. Okay, so so okay, I think I've done this. I'll tell you the idea. If that idea is not correct, then I will implement this.
Sure.
My idea is to use binary search, but I'll need two binary searches. So let's say if I'm searching for 8 in this example, what I'm going to search for, I'm going to search for 8 once, which is going to give me this index. And then I'm just going to go, okay, this is going to be my starting index. Now I want the ending position. For that, I'm going to search for 9. So I'm just going to get this 10 in that case. If a bigger item is present in the array, I'm just going to go one index back, and that's going to be my ending position.
Okay, yeah.
So I'm going
to... So I think if you've done this, that sounds pretty good. Let's do another one.
Okay.
And I'll add a little bit more time. So, okay. So we're swapping to this one.
Okay. You are given an array of integer nums. There is a sliding window of size k, which is moving from very left to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position. Return the max sliding window. Okay, by max we mean the sum, right? Let me see the example.
So not the sum, the maximum of the window.
Maximum of the window. Okay. I don't think I've done this, so we can do this one. Okay, let's take this example where k is equal to 3. Okay, and we have to return this array of which stores the maximum.
Yeah.
So, okay, when this is the current window, then the max is 3. Then it's again 3, it's again 5. Okay. I see. So, yes. Okay. Okay, let me just think. Okay. So, I'll just take 1 minute to think around, then I will share the approach. Okay, so the brute force way is just to create this window. And then once we shift the window, we just remove this last item. Okay, let's say we maintain a vector for the sliding window. Okay, this is the brute force approach. In this, we basically maintain a vector of the current window. As we move the window forward, we are gonna remove the last item from the vector, and then we can again iterate that window, the vector which is the window right now, and then see which is the maximum. So that is the brute force way.
Mm-hmm.
And then that is gonna take O of n times the size of the window. Let's say the size is k. That's going to the brute force approach here. Now, okay, now I'll think of optimizing this k here.
Mm-hmm.
If we can do better than this. So
Yeah, we can definitely do better. Otherwise, this would be like a pretty easy problem.
yeah. So what I'm thinking is we can use a priority queue or a max heap here.
Mm-hmm.
So we push this in the max heap. The max heap, the maximum element is on the top of the heap, and then I'm just gonna okay that gives me the answer right here. When we shift the window to the right, we have to remove this from the heap and push this into the heap.
Mm-hmm.
So for that, okay, so we can push this into the heap and then get the max again, but we also have to remove this. Now to remove this, there is one way where we can, search this and remove this, and again, this can be very deep into the heap in the max heap. So
Yeah,
for
like
that, we'll have
it can
to,
be middle, it can be in the end. Yeah.
yeah. So I think somehow if we can lazily remove this, should be the right way to go here.
Mm-hmm.
Lazily
And what
remove
do you
the
mean by
items.
lazily?
Yeah, lazily. Uh, since this is gonna be at anywhere in the heap,
Mm-hmm.
we can't remove it instantly right now when we are using considering this window. So we will have to wait for the right time when we can remove this. And how do we find the right time here to remove this? That is what I'm thinking right now. So, okay, and then they can be duplicates in the array, right?
Mm-hmm.
Yeah, they can be duplicates. Okay, so how do we find it? Oh, okay. I think I have an idea.
Okay.
So what I'm gonna do is I'm gonna basically store a set. Let's say I'm gonna have a set.
Okay.
Let's say, and this is in the heap. Let's say right now I have 1, 3, and -1. This is a max heap, so I easily get 3 in it,
Yep.
the max. Next time when I shift the window, I'm gonna push 1, 3, -1, and -3 in the heap.
Mm-hmm.
Now I have to remove this.
Mm-hmm.
The top of the heap is gonna contain 3, and I don't know where this is present. So what I'm gonna do is I'm gonna store this one, which is out of the current window in this set.
Mm-hmm.
And again, I'm gonna take this 3 as the maximum element in the heap. Now I'm gonna again 1, 3, -1, -3, and then I have 5. Now I have to remove this 3 from the heap, top of the heap.
Mm-hmm.
My top of the heap is 5, not 3. So I'm gonna take 5 here. I'm gonna push 3 here.
Mm-hmm.
And this way I'm just gonna go until here, where my heap contains all of this.
So I see what you're saying, but what happens with the duplicates, right? Like what happens if number is both in and you removed? Like how would your solution handle that? Like let's say it's
Yes.
just all fives, for example, just this really simple solution. Like how would it handle something like that?
Okay. So if it's all 5, then this is basically going to check off top of the heap. If
Mm-hmm.
the item that is being removed, let's say this item is 5 and the top of the heap is 5, I'm
Mm-hmm.
just going to pop that top of the heap.
So
If I pop, yeah.
okay, so yeah, so if you pop, but then what happens when you hit a 5 again? Like when you're removed from the heap, are you gonna like remove from the set as well, or are you gonna like how does that work? Because yeah, like let's say your entire thing is fives, right? So
Yes.
you would just keep popping five, like you'd be like where or whatever, right? Like so maybe some other case where like you're not popping right away. Maybe it's like uh some other thing. Like
Hmm.
basically, how do you handle the case where like you do pop, but then you might have more of them, and then like you only need to pop some, you know? Does that make sense?
Yes.
What you're saying? Like yeah.
Yes. Yes. Yes.
With the set,
So,
like you're basically saying like if it's in the set, remove. But then what if it's in the set and in your window and so on, and your window can be big?
yes. So I think instead of using set, let's say we use a vector here or a multi-set. A multi-set
Okay.
can contain duplicates.
Okay.
So yeah. So I will have, let's say this is my current window.
Mm-hmm.
Okay. And now, okay, this is my current window. So now I basically have to remove these from the heap, right?
Mm-hmm.
These are already going to be in my this multi-set. Now my current, let's say my current heap state is like this, all fives. So I'm
Uh-huh.
gonna remove until I, get. So basically, I'm gonna see my top of the heap is 5,
Uh-huh.
and I have a 5 here. So I'm gonna remove this 5. Okay, now I'll see my top of the heap is 5, and I have this 5 in multiset as well. So I'm gonna remove this.
Uh-huh.
And now my top of the heap is 5, so I'm gonna use 5 like this. So I'm gonna check if my top of the heap is present in the set. If it is present in the set, I'm gonna pop it up, and again gonna check.
I see. So basically this multi-set could be basically like a hash map instead. Either one would work. Where
Yeah.
you just need a count. Okay. Okay, so basically you're saying like if I'm at the top of the heap and I need to remove it, I will remove and then I'll just like store like a count type of thing or like multi-set same thing. And a multi-set you can just check if a number is in there and it can be in there a bunch of times. You're saying?
Yes. Yes.
Okay. Uh yeah, I feel like that works. Let me ask you. So I do think that works, but let me quickly ask you something and see if you can figure it out. So
Hmm.
basically, we just need to know like, is our top of our heap invalid, right?
Yes.
Um, so is there a simpler way we can figure out if the top of our heap invalid, right? We have this like window, and we have a top of the heap. Is there a simpler way without a multi-set? I do think your approach works though. So if you can't figure it out in like a minute or two, we can just go with this.
Okay. So, okay, that's nice. Yeah, I think we can maintain a map. We can
Okay.
maintain a map. Okay, I'll tell you how. So this is my current window. This
Mm-hmm.
is in my max heap, and this is also present in a map, in a
Mm-hmm.
hash map. So now when I shift the window to the right, what
Mm-hmm.
I'm gonna do is I'm gonna insert this element on the right to my hash map and gonna remove this from the hash map.
Mm-hmm.
Now I'm gonna check in my max heap again if the top of the element uh, is in the hash map. If it is in the hash map, then it's a valid element. We can use it.
So that's basically the same as the
Same thing.
multi-set,
Okay.
but so think
Hmm.
about like a window tells you something, right? Like in a window, you know what's not and what's like the window itself tells you like what's in it, right? Like a window has, a start and an
Oh,
end. So can you do something simpler?
yes, we can do it. We can maintain a max heap with this, with the element and with the index.
Mm-hmm.
So so let's say my current window goes from 1 to 3.
Mm-hmm.
I'm gonna see if this index is in this range or not.
Mm-hmm.
So if it is in this range, then I can use this. If not, then I'm gonna pop it. So a max
Mm-hmm.
heap of like this, which contains element as well as the index.
Yep. Yeah, and you see how that would be a little. I mean, I think the multi-set is fine too, but this is like a little bit easier. So let's
Yeah,
go with this one.
awesome. So we want to we want to return a find max, let's say, and
Oh, and before actually, one last question: what's the time and
yeah,
space complexity of this approach?
awesome. So of this approach,
Mm-hmm.
for this, we basically iterate through the whole thing, and we push it. Okay, every time we push one thing, and we pop until we pop it. So this is gonna be log of k log k. Okay. So this is gonna be O of n times log of k.
Mm-hmm. Yeah, I
Like
think that's
this.
correct. Okay, cool. And then the space is going to be what?
Space is gonna be okay. For the returning vector, it's gonna be n,
Mm-hmm.
and
Well, we can like if you don't count the
okay,
result, so
okay,
without the result. Okay, yeah, I think
it's gonna
that.
be of k. This of k, yeah,
Yeah, I
because
think
we're
that's
just
good.
gonna store the window size elements.
Okay, all right, let's get to the coding part.
Awesome. So this is the input vector. Let's say this is nums, and this is the window size.
Mm-hmm.
I'm gonna say first. Let me get the size. So first, I'm gonna get these k elements, and I also need a max heap. So I'm gonna say priority queue, and let's say I store a tuple of int comma int,
Mm-hmm.
and this is max heap by default. So
Oh,
tuple of
in C, it's a max by
it's max
default.
heap by default. Yeah.
Okay, sure.
So what I'm gonna do is pq dot push the element at this position and the index.
Mm-hmm.
Once I've done this, then I'm gonna say I is equal to k, I less than n, and I plus plus. So what I'm gonna do is, okay, so first I'm gonna push this element, which is gonna be I and the ith index in this. Now while I'm gonna say pq dot top. And let's say this is my element, comma index. While index, okay, now I also need to have a range. So I'll say start is equals to 1, and okay, no, I also need a input vector. This is my vec.
And the input vector is your like result.
Okay, so this is the input vector. This is my result vector.
Yeah, got it. Okay, yeah. Okay, cool.
And then I'm gonna say element comma index, and I'm gonna say vec dot pushback element. And now, so start is gonna be 1, end is gonna be kth index. Okay, this is my range, and then basically I just go here, and what I do is while index is less than start pq dot pop, and then I'm gonna again say what I will do is, okay, let me just say x. Oh, I see. I could have done this. I'm sorry. Okay.
That's fine.
Yeah. So, so now my, okay, this is my current range. If my top of the Where is my top? If my top of the element index is less than start, which is out of the range, we just pop it. And now I also need to update it. So I'll again say like this, pq.top, pq.pop, and it goes on like this and this. And once we are out of the range, I'm just gonna say the top of the element push back like this. And now I have to update start plus plus and end plus plus. And finally, we return back.
Okay.
I think get 0 dot first. Okay, instead I will use a pair right now because I'm facing some issues here. So pick
you
it at
can't
top.
you can't like unpack a tuple or something.
I can unpack it, but what I'm doing is I'm declaring the type 2 times here, so which is
I see.
creating an issue for me. So I'll just use a pair for simplicity here.
Okay, sure.
So pair, pq dot pushback, pq dot top gives me this.
And how does a pair priority queue work in C++? Does it just sort on the first one? If there's a tie, it sorts on the second and to max?
Yes, exactly that. Yes.
Okay.
Awesome. So, okay, let me just dry run through this and then we should be fine. So we get an input vector, and this is the window size. This is the, again, the size of the input vector, input array, and this is the response vector. We are maintaining a max heap, which contains two things, element and the index itself. For the first window, we simply push it into this, max heap. And once we have this current window, we basically take the top of the heap and push it into our final vector. Now we have a new window which starts from 1 and ends at k. And so for this, yes. So now basically, yes. So basically, we again iterate through the whole array. We push the element that we have with us, and again the range is correct for this. Now what we do is we basically take the top of the heap and check it if it is out of the bounds. If it is out of the bounds, we basically simply pop from it, and this loop goes on until we have an element which is in the range. Once we are in the range, we're basically gonna push the top of the heap, and then shift our window one step ahead, and then and this goes on until the end.
Okay. Yeah, maybe you can try running it on some test cases.
Absolutely. So let's do this. Okay, and then I'll have to iterate.
Can you not print the vector? There's no like print vector in C++?
No, you actually have to iterate and print it.
Okay, sure.
Awesome. So let me just print this.
Okay.
And so what we get is 335567. I think this is the right answer here.
Okay. So I am curious, and I don't know if this is a bug or not, but you tell me. So
yes,
on line 70, you get the element in the index, right?
Yes.
And then you're clearing things.
Yes.
And then you push back the original element in the index. So what if the element in the index were out of bounds? Like, shouldn't you get that afterwards, or am I missing something?
Okay, so when you're inside the loop, now if this element was out of the bounds, we are we'll go inside this and we'll pop it.
Oh, okay, I see. And then you're okay, got
Yeah,
it.
re-getting the
I
top.
wasn't sure. Okay. Okay, that sounds good. Okay. All right. And then yeah, I'm pretty confident this is good then. I do think you missed one case that I didn't specify.
Okay, let me think about the edge cases.
Sure.
So yeah. Hmm. Okay, so one of the straightforward edge cases is like this: when the vector is empty, in that case, and we have some value k here.
Mm-hmm.
I'm assuming this vector is empty and k has some value. In that case, this is gonna get stuck here. So I'm just gonna say if n is equals to 0, return empty vector for that case. That is gonna be one case here.
Mm-hmm.
And in a case where let's say k is bigger than nums, the size of the nums.
Mm-hmm.
Maybe I should ask you for constraints actually. Can you tell me the constraints for nums and k ones?
Yeah, so K can
Because
be
yeah,
bigger than nums, and then yeah,
okay.
that's what I was gonna mention.
So mm, I think this should be fine. Yeah,
Okay, maybe we can try it.
yeah, absolutely. Are you sending a lead code link?
Oh no. You can just make K like 10 and see what you get
Okay.
in 88.
Okay.
I
So
don't need to run
one,
it
two,
in
three,
lead code.
6. Oh, but you just said that, right? The k's value can be bigger than the num size.
It can.
It okay, it can.
Yeah.
Okay. Okay, now let me think because I thought you were saying that.
Mm-hmm.
So if k is bigger than that, okay, if it can be there, then in that case, Okay, so I think for that case, I'll have to write the code. For example, then in that case, I'll see the maximum of whole vector and then populate a whole, populate the returning vector with the maximum of the whole vector.
So what do you think we should return if K is bigger than nums? Can we ever have a valid window?
We can't have a valid window.
Right.
But if we still want to return a response, then in that case, we can take the maximum of whole input nums array and then
I
populate
see.
another returning vector of the same size and populate it with the max all over. That was what I was saying.
Well, so if you look at
Mhm.
like the example in your code, like the length of the example is like 8 and K is 3 and your result is 5 or 6 or something. So if K is 10 and the nums is like 2, then you should basically just return like the empty array because you don't have a valid window ever. Um, does that make sense?
Yeah, I think that depends on how
Yeah,
you want to set up the
whatever.
contract. Yeah,
Yeah.
yeah.
But essentially, the main thing is that would have been a good one to clarify. But I think we can move on to the next problem. I think it's
Okay,
fine.
awesome.
Okay, so let me ask you: have you done graph? Decent amount of
Y-
graph?
Yeah, we can do that. Yes.
Okay. All right. So second problem, right there.
Awesome. Okay, so we have the problem here.
Yep. Just gonna comment out this. Okay, go ahead.
So there are n people in a social group labeled from 0 to n minus 1. You are given an array logs where logs of I is this, indicates that xi and yi will be friends at the timestamp. Okay, okay. Friendship is symmetric. What that means is A is friends with B, and then B is friends with A. Also, A acquainted to person B. If A is friends with B, or A is a friend of someone acquainted with B. If A is friends with B, or A is a friend of someone acquainted with B. Okay. Okay. Return the earliest time. Okay, for which every person became acquainted with every person. If there is no such earliest time, return -1. Okay, this is a timestamp.
Mm-hmm.
Okay,
Yeah, so you
let
have
me
a
read through
timestamp and then person A, person B.
So at 0, okay, at this timestamp, 0 and 1 become friends. Okay, we have friendship like this. And then we have at this timestamp 3 and 4, 2 and 3. And then we have, okay, 1 and 5 here. And then, okay. Okay, so this is the earliest timestamp which we would return. Oh, no. 2 and 4 are already friends, and then 0 and 3. Awesome. So, okay, this is the earliest timestamp at which they become friends.
Mm-hmm.
I got it. Okay. Okay, just let me think for a minute. And
Sure.
hmm. Okay, I think, okay, so my idea is like this. What we can do is I don't remember the exact term for this, but I know the logic. So I'll explain the logic for this.
Mm-hmm.
So initially, okay, so all the friends are from 0 to n-1. So what we're going to do is, uh, so we're going to say, we're going to maintain this vector, this array, which basically says I'm only friend of myself.
Okay.
And then what we're going to do next is basically whenever I'm basically going to iterate through whole of this, and at every moment, okay, now this is sorted or not, let me see. Okay, so what I'm going to do is first sort this based on the timestamp.
Okay.
So once sorted, I'm basically going to have this vector which basically says 0th friend is only friend of 0, 1
Okay.
is only friend of 1. And then what I'm going to do is I'm just going to iterate through this one by one. And when I say 0 comma 1, in that case 0 comma 1, in that case I'm going to see what is the parent of 0 and what is the parent of 1.
Mm-hmm.
Since now I have to connect this, what I will do is I'll make the parent of 1 as 0. I'm basically connecting this graph like this, 0, and then 1 is connected to 0.
Mm-hmm.
And then I'm going to go to next element, 3 and 4. 3 and 4, 0, 1, 2, 3, and 4 again -1, -1. So I'm going to say for fourth, okay, this is not fourth, this is fourth. So fourth parent is now 3, and 3 is, so now 3 and 4 are connected in one graph like this. And now similarly for 2 comma 3. Okay, now let me come to the main idea here. Basically, now if I want, so now let's say I have two trees, 0, 1, and 3 and 4. And now let's say at some timestamp 0 and 4 become friends, or let's say 1 and 4 become friends. Then what I'm going to do is I'm going to do this. I'm going to check fourth parent, it's 3, and one's parent, it's 0. So I'm going to connect those. So that means at the 3's parent becomes 0.
Okay.
So this way the whole graph connects. And so in the end, if all of them, I mean, if at any timestamp I see that all of them are connected, then that's my answer.
And how do you
Right?
know if they're all connected?
How do I know if they are all connected? Okay,
Mm-hmm.
so after that timestamp, I would never see a case where I have to merge these trees. So I'm gonna let's say at k timestamp, I got the first instance where I don't have to merge it.
Mm-hmm.
And as I go forward, if at any timestamp, if I don't get any case where I have to merge these trees, then k becomes my answer. And if I have to merge it, let's say at k plus 2 I have to merge it, then I will use k plus 2 as my reference time.
I see. So
Then
basically, you're storing the latest time where you had to do something.
yeah, yes,
Okay, and let's say so you get to the very end. So how do you
yeah,
know at the very end, like if everything is merged or not?
yes. So for that case, what I'm gonna do is I'm gonna basically check. I'm gonna iterate through the whole array
Mm-hmm.
and check their parents. I should get only one parent. If I get multiple parents, then the trees are not merged.
So you're saying like at the very end, all the parents will be the same number?
All of them are gonna have one parent. So the parent is gonna be just one.
So by one parent, do you mean they're all the same parent, or well, like what do you mean one parent? Because like they always have one number in here, right? So what can like if I have like this at the end, let's say I have
Hmm.
like is this valid? This is like they all have one parent, or does it have to be like this type of thing for it to be valid?
Yes, a thing like this. So we are gonna maintain. We're gonna do this thing as well. That I'm not getting the actual term for this, but the idea is to basically update their parents as well as we go on.
Okay.
Are you getting my point?
Yes. So I think this is good, but I want to ask a couple questions.
Yes.
One, how do you know like so I have two things I need to like first of all, will this ever be this like so let's say you have like zeroth parent is like one parent is one, two's parent is like two, and three's parent is two or something, right? So
Yes.
so now I want to connect one and two. So
Yes.
no matter how I do it, I'm either gonna make these both one or make these both two. Let's say make them both two. I still don't have all of them being the same, even though they are technically all connected now. So how do you handle that? Does it make sense what I said?
Okay. So we are saying zeroth parent is one. One's parent is two.
So
Okay.
let me write this
Yeah.
down to make it easier. So
Yes.
zeroth parent is one, one's
Hmm.
parent is one,
Hmm.
two's parent is two,
Hmm.
and three's parent is two. So basically,
Yes.
like two and three are connected, zero and one are connected,
Yes.
right?
Yes.
Now I want to connect one and two, and basically you said like I'll just make, either one's parent two or two's parent one. But no matter what I do, I'm never gonna have it all the same number, like what you said, right?
Yes. For that, okay. Let me. Mm, so this merging is always going to happen like this. I'm always going to make the smaller element as the parent,
Sure,
smaller index as the parent.
sure. But even
So
then, you can still have the case where, like, if I say like merge zero and one, merge
yes,
two and three, and then merge one and two.
yes,
So basically, zero and one would have like zero, right?
yes,
Two and three would have two. And when you merge
yes.
one and two, you're going to say, well, I'm going to pick the smaller one, so it'll be this. And you still have the same problem where, like, you said they all have to be the same, and they're not.
No. Okay. Let me see. So zero initially -1, -1, -1, and -1. When we merge this, one's parent becomes zero. So this is going to be zero.
Mm-hmm.
And when we merge this 2, 3, so this is going to be 2 here. And when we merge 1, 2, I'm going to see what is one's parent. One's parent is 0.
Mm-hmm.
And what is two's parent? It's nothing. It's 2 itself.
Mm-hmm.
So what I'm going to do is I'm going to do it like this. Now, now, now what I'm going to do is now I'm just going to iterate through the whole thing. Iterate through the whole thing one by
Mm-hmm.
one. Now when I see what is three's parent? Three's parent is 2 and two's parent is 0. This is also going to become 0.
I see.
In the last, when we iterate through the whole array, this is going to sort. This is going to sort this
So
whole
you're
thing.
doing like like when you figure out the parent, you're like going down recursively to the last, like to the top level
Yes,
parent. I see.
yes, yes.
Okay, yeah, I think that works. I think you can code it. I think it makes sense to me.
Awesome. So I'm just gonna reuse this part so that we can save some time here.
Oh, and before you code, actually, so what's the time and space over this one?
Okay, so so the time for this is gonna be uh, so we iterate through the whole vector,
Mm-hmm.
this array one by one, and find its parent. And this is gonna happen recursively, but we also do the caching thing at the same time. I mean, uh, uh, I think I can explain the caching term later on, but this is gonna be of say in the worst case, the whole vector is like this.
So there's like an algorithm that you're doing that this
Hmm.
is called. Do you know what
Yeah,
it's called?
disjoint
Yeah, so
sets.
for disjoint sent, do you know the time complexity of basically, so there's like two things you're doing, right? There's a find
Yes,
parent and then there's like a union.
yes.
And so what's the time complexity of each of these?
Okay, okay. So, hmm, I think okay. Let me see the time complexity. Okay,
Mm-hmm.
so this is gonna be n times. Okay, so now I basically find it recursively, and then I also cache this out in the union in the find. Ah, hmm,
I think let's come back to it after you code. I just want to give you time to
okay,
finish coding because we have like 10 minutes left. So let's
awesome.
code
So,
and then come back.
okay, awesome. Thanks. So, yes. So we have these vectors. Let's say the vector of vectors nums, and then we want to basically see the latest timestamp at which they are that. Okay, so I first need to sort this out. Nums.begin, comma, nums.end, comma. This is gonna be like this. So we want this to be in a of 0 and like that, and b of 0. So smaller timestamp is gonna be before it. Awesome.
Okay.
So yes. Awesome. So okay, I think this is good. Now, once we have sorted this out, what we want is we want basically to iterate through the whole thing, and then okay, now we want two things. Uh, Let me create a parent vector, which is initialized by n comma minus 1. Once we have it, what's next? We basically want to perform find and union operation here. So, okay, let me say void int find, and I'm gonna say parent of this current item. So let's say my current item is this, and vector int and parent, and if parent of item double equals to -1, then return the item itself because it is itself its parent. Else it is not. Then what I'm gonna do is find parent of item comma parent like this, and then return parent of item. And then I also want to do the merging part where we, let's say, union. And in that case, okay, let me int a, int b, and we also need this vector int and parent. If parent of a is equals to parent of b, then simply return. Else we want to see what is the parent of a, which is gonna be find a comma parent, int parent of b, which is gonna be find b comma parent. And now what I'm gonna do is parent of b is it's gonna be parent of a, and then return simple. Yes, awesome. So so what we do is, for now I'm just iterating through the whole vector, so which is gonna be like nums and I plus plus. Now what we do is we basically have int timestamp. This is nums of I of 0, and then I have a, and I also have b, which is going to be like 1, and this is going to be like 2. Then what we do is we basically have to merge them. So I will do union of a comma b comma parent like this, and this is union underscore because union is a okay. Awesome. So yes, and I also need a timestamp. So let's say min time is equals to, let's say this is max int. Why is max int not here? Okay, let me declare some variable for this now. Why is this not working?
I don't think you even need max int. You can just make it like 0 because like you're just storing the latest timestamp. You don't need to do a max. You can just make the time like if like basically what you were saying is like you're gonna check if you needed to do something, and if you did, then store the timestamp, right? So
yes.
yeah. Okay.
So I'm checking if some union was done or not. If the union was done, then we basically okay. I think we can just store the time as well. So max time is just going to be the time, and then we simply return the max time.
Okay. You also mentioned you're gonna check like if everything was correctly.
Yes.
Yeah.
Yes. So now I can basically go through the parent array one by one, and what I can do is I can basically yes, parent of this item is just gonna be find item comma parent. So this is gonna be like I comma parent.
Okay.
Yeah, and now what we want to do, okay, they can, okay, why I see why you're saying that, because there can be a case when there's no such acquaintance that all of them get acquainted with each other or not. So now once we have all the parents in this, okay, so what I'm gonna do is I'm just gonna say, let's say I have a set, and I'm just gonna say set dot insert parent of I, and I'm just only gonna insert if parent of I. Oh, okay. Okay. If parent of I is not equals to -1. No.
Okay.
Okay. No. Okay, we can just do this like this. If yeah, if st dot size is greater than 1, then return -1. Else return. Why is it? Okay, this is like because of this. Else return the max. time. I think this should be it. Yes.
So, so for a correct result, one number will have its parent as -1, right? And then the rest will have that. So, like, for example, this is valid, I think.
Yes, this is valid.
In your case, and
Yes.
this set size would be 2.
No, it's going to be okay. Yeah, actually, this is what I was thinking about. In this case, this is going to be 1. I'll tell you why.
Mm-hmm.
Because if we see the find, if it is -1, then it returns the item itself.
Ah, okay, got it. Okay, yeah, sounds good.
Yeah.
Cool. Makes sense.
Okay, let me run this.
Mm-hmm.
Okay, let me try run this because I haven't written the approach anywhere. So awesome.
Sure.
Okay. So what we do is we basically have this integer, this nums array coming in, and this is the what is this? This is the what is this? Why do we have n equal to 4 here?
Yeah, I don't think. Was there even a K in the input?
Oh,
No.
okay. We're
Oh, there
getting
was
n
an
as well.
N. There was an N in the input.
Okay, we don't need this. I mean, if we want, we can take this like this. So we're good either
We
way.
do need it because N is not equal to num size necessarily, right? So, like, there can be 10 people with like one meeting. So, yeah.
Oh, okay. I see. I see.
So, but
I
you
got
are
it.
given this N, so I think if you're using
Hmm.
it correctly everywhere, so I think you should be fine. No,
Yeah,
you
yeah.
probably not. You probably need to do like, or are you? Maybe. Yeah, I'm not sure.
Yeah, this is
In
correct.
some places you need to use the nums, in some places you need to use N.
Oh, yeah,
Like
right.
here needs to be nums. I think this is N. Yeah, I think that's correct. Okay.
Awesome. So what we are doing is we're basically having this parent array, which basically stores the parent of any element, and it can only have n people. So this is 0 to n-1, so this becomes n people. We are basically sorting it on the first timestamp, and then we have this vector which stores the answer, this integer which stores the answer. Then we are simply iterating through this nums vector, getting its time a and b, which are the two people. We are performing union on it. If we perform a union on it, then we return true, else we return false.
Mm-hmm.
How do we perform union? We basically get the parents of both of the people, and then we basically perform the union here.
Okay. Yeah. So I think
And,
I get I get the rest of it.
hmm,
Let's just try to run it and see if we have any bugs because we're a little low on
awesome,
time.
awesome, awesome, awesome. So this is my logs. What I'm gonna do is I'm gonna do it like this. Oops. We're almost done. So why is this? Okay, this isn't because this is vector of vectors. And let's say this is the nums and find max nums, and in this case it is 6.
Yeah.
And
Okay.
and we are returning a time. So int, I'm just gonna directly do it like this, see out
Sure.
this, and we are good here.
Okay.
Okay, let me run this.
Mm-hmm.
And the answer should be okay, this is some type issue in this, which shouldn't be an issue, but I'll just do this for now. No, okay, the answer is wrong. We are getting -1 here because I think we have something in the set. I can quickly see what's in the set. Wait, what? The merging didn't happen. 0, 1, 2, 3, 4, 5.
So just because we're a little short on time, I do think this is a bug because you need to call find first.
Yes, that's correct. I think this is the bug.
There might be more, but that one's kind of tough to find. So
It should return the timestamp now, which is, yeah, that was a bug. So, okay,
okay,
let
all
me
right,
run this on the exam.
sure.
Okay. Do you?
Yeah, I think we can just stop because you're a little bit over already.
Yes.
So let me give you the feedback. Okay, so
Hmm.
going back to the first one, so you talked about the problem. You didn't mention the K thing, which is like the only constraint. So I definitely would have liked to see that, because like you said, if K is too big, maybe the empty array is correct, maybe, the biggest number is correct, whatever. Clarify that. I think that's just like 3 points. Yeah. And it does kind of suck if like you write all the code and then you're testing and you're like, yeah, but what about this? Like would be a lot better if you see that like earlier.
Hmm.
Let's see. So you figured out the heap. You figured it out. I also kind of probed you towards like a cleaner way of doing it, even though your way works too. So you're familiar with like multi-set, a bunch of other approaches, lazy heap removal, which is like not super simple. The optimal here would have been a deck, but if you haven't seen this problem, like for an interview, this is a hard question already. So I think a heap's totally fine. You can look into how to do like a deck for a min and max of a sliding window. You basically just have a monotonic queue, and then you just like then the front of your queue is always the min or the max or whatever way you want to do it. But I think this is fine as well. Your time and space was correct. Your coding was good. I think your code was pretty clean. Could have been a little bit cleaner. You could have like combined these loops and stuff. But this is like pretty good. Your variable names were fine. So yeah, coding could have been a little bit better, and I think yeah, but it was like pretty good. Let's see. So you walk through the code with your example. You tested the edge cases. I don't remember if you had bugs. I don't think so. I want to say. Um, and then yeah, I wrote you had no bugs. And you discussed potential optimizations basically when I probed you in the other thing. So it's good that like you're able to come up with a solution, but if I probe you towards something that you didn't come up with, you can still kind of like get there pretty quickly, which is good. So for this one, I rated out of 5. So your problem solving is a 4 out of 5 because like Optimal's deck, you came up with heap pretty good. Coding 4 out of 5. Once again, could be a little bit cleaner, but pretty good. DSA, you knew multi-set heap, lazy removal, all the time complexity stuff, so that was great. So that was 5 out of 5. And then communication 5 out of 5 as well. I feel like you are very good at like explaining what you're doing. I never really have to wonder like where you're at. So I think that was very good. So this would be like if I had to give it like weak hire to like solid hire to strong hire, I'd say this is like a solid hire. Like you didn't like I don't think you can have like a strong hire unless you get the optimal thing, but it was definitely like no, I don't think it was a weak hire. I think it was like quite solid. Any questions
Hmm.
on that one?
No, we are good. And thank you for your feedback. It's helpful.
Okay.
I'm gonna check out that deck thing. So
Yeah. In the second one, so you restate the problem once again. You talked about input edge cases. You didn't really mention like what would happen. I think you didn't ask if the timestamps were sorted, but you sorted anyway, so it's like whatever, it's fine. I would definitely. I think that's a good thing to do. Either ask or I'd probably just ask because like what if they are then like well actually, I guess in example two, they no, in both examples they are, but yeah, I'd probably ask because like if they are, then you don't have to sort, and then that saves you some time. For the second one, let's see. So you did come up with basically union find. I was like, okay, this is kind of union find. So there's a couple problems with it. For one, and you kind of did some of it. Like your find is recursive, um, but one of the problems is you. So typically with a union find, you want to have a ranks because like as an example, let's say you have like 0, 1, 2, whatever. I do think this like optimizes it, but basically the idea is like you want to. you want to add the smaller tree to the bigger tree instead of the other way because it's like cheaper. So you can look into that, like union find path compression. You kind of did some of it, but basically, I think you need a ranks to. And then basically, if you have ranks and you have path compression, then your find and your union. I asked you like what's the time complexity there. They're basically O of one on average, if you have everything. And you almost had it, so I think. And union find isn't like a standard algorithm; like it's more complicated, I guess. So I would definitely like review it a little bit compared to what you had. And also, I had to point out to you the error, which is, yeah, but that one
Yeah,
is like a pretty common one, so it's not too bad. Let's see. And then you talked about what you were writing, and you had like good names and stuff. Let's see. Yeah, so I pointed out the bug you had, and then yeah, the not optimal because you need like ranks and you need to add smaller trees to the bigger trees, but also it's not the biggest thing. Like it's mostly right. Um, and then I think like edge cases would be fine. Um, and then you walk through the code with an example. You tested, and you didn't have time to fix all your bugs. So you did kind of like we went a little bit over. I think we went a couple of minutes over. So I think for this one, I would say your like problem solving is pretty good. Probably like a 4 out of 5. Not like the best. I'd say DSA was this one was a little bit weaker. I'd say like 3 out of 5. This was a harder algorithm for its worth. Like you identified the algorithm, but you had some gaps. And then your coding was probably also like a 3 out of 5. You had some bugs that to point out to you, and then your communication I think was also like very good almost always. So I think that's like a 5 out of 5. So for the second one, I'd probably say is like a weak higher. So like for the first problem, I'd probably say like uh, solid higher, and then for the second one, weak higher. If I had to give like an overall score, I'd still say like solid higher. Granted, because like I do think this problem is like not a common algorithm, so I feel like if I ask a not a common algorithm, then I can kind of give you a little bit more room for error. You know, if I ask you like a sliding window and you don't know it, that's like a red flag. But if I ask you like Dijkstra's and you have a bug or two, or this one and you have a bug or two, it's like nothing major, then it's like pretty good still. So I would say, yeah,
hmm.
like overall, I'd say this was like a solid higher in my opinion. Even though you had because you literally just had the one bug that I had to point out to you, and I think that yeah, it wasn't written like optimally, but for the most part, it's pretty good. And there's like some few things you can brush up on. Like if you just look up how a union find is written, it's like you need like 3 more lines of code, and your solution would be fine. Um, and
Yeah, I'll
then
revise through it. Yes.
yeah, and
Yeah, I give
it
it that.
seemed
Yeah.
like
Hmm.
you were familiar with it, but you were kind of like I don't remember it exactly, like that kind of thing. Was
Yes,
what I was
I think
getting.
I'll have to. Yeah, exactly. I'll have to revise it.
Okay.
Yes. Hmm.
But yeah, I mean, you can just look at it again. I do think Union Find is worth learning because some problems, like this problem, I don't even know if it's solvable without it, to be honest. And it makes a lot of graph problems easier that you'd have to use like a DFS or something. And honestly, I don't
Hmm.
think it's a complicated algorithm, so I do think it's worth like brushing up on, knowing time complexity. And so yeah, it's basically like yeah, the time complexity is basically O of one for both of these on like amortized. Like some calls are longer, but on average it's like O of one if you write it all correctly. And then yeah, and the other thing you could have done, but it doesn't really matter, is so union find you have like number of components, right? So like you have like 6 items, they're all a component. So what you could have done to make your solution a little bit easier was like just keep track of the number of components, and then as soon as you go down to one, then you know like everything's connected. So you can just like keep track of components whenever you do a union. If you every time a union's successful, you subtract one, because basically a union takes 2 components, turns them into one, and then you can just say like, okay, when I have one component, that timestamp I can just return. And then you can like return a little bit faster, and like let's say there's everything's connected and you have like a million timestamps, and you can just return way faster. So yeah, does that make sense?
Yes. Yes. Yeah. I think okay. I didn't knew that. Okay. I mean, this is a good way of thinking about this.
Hmm.
Yes.
That's also a common way for a lot of these union find problems to figure out if everything is connected or if it's not, or how many things. Just make a components variable and keep track of that, and then yeah, helps a lot. Uh,
Awesome. Yes. Hmm.
okay, but yeah, I'd say this was pretty solid. I feel like the first one was also pretty solid. I think the first one's like a weak higher, so this one's kind of like a medium higher. So yeah, definitely, it's all small things. Just brush up on the small stuff, and I think you're pretty good. Also, I do think this was a harder interview for what it's worth. You did have like 50 minutes. Like the first problem was a hard. The second one was like a solid medium that most people don't know because most people don't know you need fine. That's why I asked if you knew graph, because it's like
Hmm.
if I ask you this, you don't know graph, then we're just like wasting our time. So yeah.
Hmm.
So yeah, I'd say this was pretty solid, and yeah, keep up the good work. Brush up the little things, and I think you'll do fine.
Awesome. Thank you so much for your time.
Okay, yeah, no problem.
Thank you.
Okay, bye.
Bye.